Assalamualaikum and good evening. We are from Team 7 presenting about our Team Mini Project Air Quality Checker and Monitoring. So the SDG for this project is Smart Environment and Energy, SDG 13. This is the team members. So for me, my name is Muhammad Haziq bin Maizal and I am in charge for hardware and sensor integration. Second member is Hong Hui En, which is the person in charge for IoT communication and dashboard and cloud. Also, the last person is Sophia Anis Azizan for data analytics. So the background for our project is that indoor air quality significantly affects our health and productivity. Yet harmful gases like CO2 and smoke are often invisible and hard to detect. So most people nowadays spend their time inside or indoor, making it essential to track environmental changes like temperature and humidity in real time. So the problem statement for our project is that common household pollutants are impossible to see or smell, meaning people are unaware when their quality is it good or poor quality. So the objective for this project is to monitor indoor quality, air quality, temperature, and humidity in real time, and display the data from the sensor to an IoT platform that provide instant visual warnings. These are the circuit diagram and the enclosure design. The component that we use for this project is ESP32, which has the Wi-Fi connection so it is very essential for IoT project. And then for the sensor, we use two sensors, which is DHT22 for temperature and humidity detection. And then for the gas sensor, we use MQ135. And for the visual warning, we use two LED that indicates the air quality, the green color and the red color. So these are the flowchart. As we start our project, the initial setup will begin, and then Wi-Fi connection, if connected, the sensor always start integrating. If the Wi-Fi is not connected, it will have 500 milliseconds delay and retry connection. So after the DHT begin, it will read temperature and humidity, and then the MQ135 gas sensor will start calibrating for 60 seconds to get a stable reading for gas sensor, and then it display the DHT22 will start display temperature and humidity. If the gas quality is below 200, the status will come out as good air quality, and the green LED will start turning on. If the gas sensor, if the gas filter or the gas reading is somewhere between 200 and 400, the status is moderate. So both LED, green and red, will start turning on. If the gas readings is above 400, the status is poor, and the red LED will start turning on. So all of these readings and from sensor will be sent to ThinkSpeak for 2000 milliseconds delay, and the system will start looping back. So I will be presenting a live demonstration on how my air quality checker and monitoring works. So this is the hardware for our mini project. So we use two sensors, which is the DHT22, the MQ135 gas sensor, and then these are the circuit we use, not MCU ESP32, and then we have the LED, the red and the green one for the instant visual warnings. Okay, so how does this project works? When the gas detect as a moderate quality, it indicates two LED which turn on, red and green turn on at the same time, so the status is moderate. So the gas filter is around 200 to 300, so the gas filter right now is 318, and the temperature is 28.90 Celsius, and the humidity is 68%. So if it indicates good status, the green LED will turn on and the red LED will turn off. If the air quality is poor, the red LED will turn on and the green LED will turn off. So how we get the gas sensor reading is we use a low pass filtering method, which is we set the alpha value for 0.3 or 30% of the gas raw value, and then we we add in with 1.0, we add minus with the alpha value to get the gas filtered or the new value of the gas filtered. So that is all for my part. Thank you.
Okay. Good evening, Doctor. I'm Ong Hui Eun, and for my part, I'm responsible for the IoT system architectures, connectivity, and data flow of the device. This includes how the sensors communicate with the cloud, how the data is processed, and how notifications are delivered to the user. So for the IoT architecture overview from the flowchart, our system follow the typical IoT architecture consisting of a sensing layers, a connectivity layer, middleware layers, and applications layer. In the connectivity layers, the ESP32 acts as the IoT node and communicates wireless using Wi-Fi on 2.4 gigahertz and 802.11 for the bandwidth. The communication between the ESP32 and the cloud use TCP or IP, and the application protocol is HTTP REST API for uploading data to the ThinkSpeed. For cloud processings and visualizations, we use ThinkSpeed. 4 fields are mapped to the temperature, which are temperature, humidity, air quality, and the status of the air. So the cloud store the historical data and perform time series visualizations so the trend can be analyzed. And additionally, I have put the alert systems. So when the pollution status change to poor, our device will trigger a Telegram bots API to send an instant alert to the user on their mobile phones. So for the data processing, which is edge computing, it is to handle the noise from the MQ135 sensor. We apply a low pass filter at the edge node. So we also perform the threshold-based classifications. So this can reduce the cloud computations and enable local real-time decisions such as turning on LED and sending alerts. So the IoT design considerations, the wireless range for the ESP32 Wi-Fi is typically in 10 to 50 meters in the indoor, and there is a attenuation source such as wall, furniture, human body, and suffering that will affect the signal strength. Mm, mm. So there are two latency paths in our system, which is cloud visualization on ThinkSpeak, which update every 15 to 20 seconds due to the platform rate limits, and Telegram event alerts, which arrive within 1 to 3 seconds. Therefore, cloud is suited for historical monitoring, while Telegram is suited for real-time warnings. And this is a diagram that the Telegram send the notifications when the air quality is poor. And this is the range for the signal strength. In the system, I also have do the reliabilities and fault tolerance. So when Wi-Fi is not connected, it will reconnect to continue the next part. And the event drivers alerts avoid transmission spam. The local LED will continue to indicate status although the cloud is unavailable. The diagram for the effect of distance on signal strength, when the Wi-Fi is close to the microcontrollers, it will show the the RSSI is negative 37 dBm, like about 10 meters. And when it is 15 meters, it will going to negative 54. And when it is far away from the microcontrollers, maybe 20 meters, and it will show the negative 70 dBm. Now I will present the examples for the latency behavior between the microcontrollers send the data to the ThinkSpeak. When the data update in the Arduinos now is 11:33, and the ThinkSpeak will also update the latest data after 15 seconds. So this is because there is the platform rate limit that we're using free ThinkSpeak, which is 15 seconds. This is the ThinkSpeak dashboards, and this is the four mappings from the DHT22 is temperatures, humidities, and the MQ135 gas sensors and the air status. And these are widgets to show the status of the air. When it is poor air condition, it will be red, and when it is good air condition, it will be greens, and when it's a moderate air condition, it will be yellows. So the temperature and the humidity is also displayed as in a value form.
Okay. Hi, good evening, Doctor. My name is Sophia Anis binti Azizan, and I want to present data analytics. As you can see, we have graph number 1, 2, 3, and 4. So for the first graph is temperature analytics. So temperature versus time. So here I use 3 times, that is morning, afternoon, and at night. As you can see, at morning the temperature is quite low. In the afternoon the temperature spikes up a bit because afternoon is temperature rises up, but at night it goes down back. Next is the humidity table. So for humidity, when humidity rises, temperature is low. So at morning, the humidity rises up. Afternoon, it goes down, and at night, it comes back up. Next, table 3 is for air quality ppm versus time with fixed threshold. So for good to moderate, we put 200, and 400 is for moderate to bad. So as we can see, mostly the data is around moderate. A very few is around good, and also there is some above bad. Okay, for table 4 is status distribution. This table is just to show the count for good, moderate, and bad data that is in the system. Okay, for diagnostic analytics, why did it happen? First, why afternoon temperature rise but humidity low? Because afternoon heat increases, hot air can hold more moisture, so relative humidity percentage drops. Why ppm goes over 400? Possible causes is smoke source occur, like burning, cooking, or pollution. And also less airflow means smoke stays longer. And MQ135 is sensitive, so spikes can happen. So in conclusion, more smoke plus less ventilation equals to rises ppm. So from the data we see, we can see that air is mostly okay but not clean, and sometimes can become unhealthy for us. So for predictive analysis, I just use from our observation from the silent analysis and the graph table. If the environment stays the same, moderate will remain the main condition. Bad spikes will happen again when smoke increases, and if no ventilation, means bad condition lasts longer. For prediction, bad events will repeat when smoke sources repeat. Okay, next is prescriptive analytics. What should we do? When ppm rises to 400 equals to bad, we have to turn on the fan or increase the ventilation, or open window or door, same to increase ventilation. Or we can also add a trigger alert, LED notification, or buzzer system. But great idea, add battery plus power indicator for portable monitoring. Not only at home, you can use it at your room or living room or the kitchen or anywhere. Okay, so in conclusion, temperature peaks in the mid-afternoon, humidity drops when temperature rises. Next, ppm mostly moderate, but bad episodes are detected. Last, status pie chart proof pollution exists in the smoke area. Okay, after I downloaded the data from ThinkSpeak, I use Scilab to extract the data using CSV file. So this data, I read the columns and extract the data from the file. And it is cleaning a bit, so no sudden spike happened to the data at the graph. Okay. You can choose whatever data you want. So I choose the smoke area. Okay, as you can see, there is 4 table. For the first table is temperature versus time. The second is humidity versus time. From the system, it already filtered, so there is no sudden spike. Therefore, graph number 3 is air quality ppm also have been filtered, so there is no sudden spike here. As you can see, the threshold appear, but only for bad, because good to moderate is 200, right? So it is inside the line here. For pie chart, it's still the same, just to show the count. So my total data is 300. For status distribution, good is 2, moderate have 232, bad got 66. Okay, and I think that is all from me. Thank you.